Welcome back to the deep dive. Looks like we're going deep on causality science today. This is a really fascinating topic. From the looks of the material you all sent over, you're trying to get at the why behind things, not just like simple correlations.
Yeah, exactly. We're trying to move beyond just observations
Yeah.
to, actually understanding the mechanisms. Like he said, the barometer change, right? But what does that actually mean? What's the cause and effect there? How do we express that?
There's like, how do we move beyond like just seeing that something happens
Yeah,
to actually figuring out the underlying reason, the cause?
right. Right. And we all have intuitions about cause and effect. That's how we kind of navigate the world, right? But how do we make it rigorous? How do we make it scientific?
From what I've been reading, it seems like this deep dive is going to equip us with some pretty powerful tools to answer those questions. Causal diagrams, do calculus. I've got to say, it sounds a bit intimidating, but also really exciting.
It's not as complicated as it sounds. Think of it like learning a new language, a language for asking what if.
What if? Okay, I
Yeah.
like that.
Yeah, like what if we change this policy? What happens? What if we take this medication? What if we, could design AI systems that understood cause and effect? What would that look like?
Okay, yeah, now I'm really intrigued. So let's start with Judea Pearl. He's a big name in this field, right?
Mm.
His book, The Book of Why, seems to be kind of like a foundational text for this whole causal revolution.
Pearl's work it's really groundbreaking. He's making a pretty bold claim, actually. He's saying that causality, this thing we think of as being all fuzzy and philosophical, can actually be mathematized.
Wow. So wait, hold on. Are you saying we can actually have like equations for cause and effect?
In a way, yes. And that gives us this precise framework for separating real cause and effect relationships from just like random associations, correlation.
Okay, so that's a huge difference.
Yeah.
And I imagine that has enormous implications for, well, I mean, everything, right? I mean, from
Wow.
medicine to like economics to AI.
Exactly. It touches every field where we're trying to understand why things happen.
So how is this different from like traditional statistics? I mean, I always thought statistics was all about finding relationships between things.
It is. But traditional statistics is really good at identifying correlations. But it kind of falls short when it comes to actually pinpointing causation.
Okay, I think I see what you mean. So like classic example, the barometer and the storm, right? We can write equations that show how like barometer readings are correlated with atmospheric pressure, but those equations, they don't tell us which one is actually causing the other.
You got it. It could be the barometer causing the storm, or the storm causing the barometer to change, or something else entirely causing both.
So it's like traditional statistics might say, hey, these things are connected, but it can't tell us like which one is the chicken and which one is the egg.
Precisely. And that's a problem, especially when we're trying to, make decisions, develop interventions. We need to know what to change in order to get the outcome we want.
Right, right. So we can't just rely on correlations. We need to understand the actual causal mechanisms at play.
Exactly. And that's where Judea Pearl and his causal diagrams come in.
Ah, yes. The causal diagrams. From what I understand, these are kind of like visual blueprints for understanding these cause and effect relationships, right?
Exactly. Arrows, dots, representing the flow of causation.
So we can actually see how these different factors are causally related.
You got it. And that's where do calculus comes in.
Do calculus. Okay, so this is where it gets really interesting.
It's a powerful set of mathematical tools that work with these diagrams to help us answer those what-if questions.
So if we want to understand, say, the effect of a new drug, right?
Mm.
We could use a causal diagram to map out all the potential factors, like the patient's genetics, lifestyle, other medications,
Right.
and then use do calculus to actually estimate what the drug's specific causal effect is.
Exactly. We can isolate the effect of an intervention even in really complex systems with tons of factors interacting. Traditional statistical methods, they often struggle with that.
This is like a superpower, isn't it? Being able to ask what if and actually get a reliable answer.
It is. And there's another advantage over, say, like deep learning approaches.
Mhm.
Adaptability. If you have a causal model for, say, how a drug works in one hospital setting, well, because it's based on those underlying causal mechanisms,
Mhm.
you can actually apply that same model to a different hospital with a different population without having to, like, retrain the whole thing.
So it's not just about fitting a model to a specific data set. It's about understanding the underlying principles of how things work.
Exactly.
That's really powerful. Now, you mentioned earlier that Pearl actually outlines 3 levels of causal understanding, this ladder of causation, right? Seeing, doing, and imagining.
Oh, yeah, that's a really useful
It's
framework.
like we're climbing a ladder, like insight, right? Starting with just basic observations, then moving to interventions, and finally to like the realm of counterfactuals and imagination.
I like that. Seeing is that level of associations.
Yeah.
Just noticing that things happen together. A lot of deep learning operates at that level, actually. Then you have doing, which is about interventions, actually changing something and seeing what happens.
Right. So like instead of just observing that people who drink coffee tend to live longer,
You actually do an experiment.
you give some people coffee, some people not, and you see what the difference is.
Right, and that requires a deeper understanding of cause and effect. You have to know what to manipulate to get the effect you're looking for.
And then there's imagining, which, I mean, that sounds like the most, well, the most human level, right? It's where we get into counterfactuals.
Yeah.
Asking, like, what if things had been different? That's how we learn from the past, how we make decisions, even how we assign moral responsibility.
It is. It gets to the heart of like human cognition, and it's a fascinating and complex area of causal reasoning that we'll definitely dive deeper into later on.
Okay. Yeah, I'm looking forward to that. Now, all of this might seem like it's like a recent development,
Hmm.
but you know, the quest to understand causality, it's actually got a long and interesting history, right?
Oh, absolutely.
You mentioned Sewell Wright earlier, a geneticist who pioneered this method called path analysis back in the like early 20th century.
Yeah, Wright was he was a real visionary, but his ideas they were met with like a lot of resistance at the time.
Ah, so even brilliant minds can face pushback when they,
Yep.
challenge the status quo. So what was he trying to understand with this path analysis?
He was studying guinea pigs.
Guinea pig.
Yep. He wanted to figure out all the different factors that influence their birth weight, like how much does the gestation time matter? What about the size of the litter? He was trying to untangle this whole web of causal relationships.
It sounds like he was trying to understand these real-world processes, not just like patterns in the data.
Yeah, exactly. He was really pushing the boundaries of what could be known about cause and effect. And honestly, his work laid the foundation for a lot of the causal revolution we're seeing today. It's amazing how these ideas that were kind of fringe back then are now becoming so central to science and, well, to just understanding the world.
So we're seeing how this isn't just some like abstract theoretical concept.
Right.
It has the potential to unlock some really profound insights into how things work.
Yeah, absolutely.
And those insights can have some very real consequences.
For sure.
Okay, well, this is already pretty mind-blowing, and I have a feeling it's only going to get more fascinating from here.
Oh, yeah. Just wait. There's a lot more to explore. We're just getting started.
So, we're talking about all these like these powerful tools for untangling cause and effect, right? But I can't help but wonder about those times when things get, a little more complicated. Like, what about when there's all these different factors interacting? How do we deal with that kind of complexity?
Well, that's where understanding confounding comes in.
Yeah.
Confounding is when you have this hidden variable and it's influencing both the supposed cause and the effect. So it makes it look like there's this direct link between them when there really isn't. It's like, Have you ever heard that saying, correlation doesn't equal causation?
Oh, yeah.
Also, this is a perfect example of that. Like, ice cream sales and sunburn rates, right? They both go up in the summer.
Right.
But it's not that ice cream is causing the sunburn.
No, it's the hot weather. Right.
Exactly. It's the hot weather that's causing both. So the hot weather is the confounder.
Right. Okay. That makes sense. But like, how do we actually like identify these confounders? And then like, once we've identified them, how do we account for them in our analysis?
Well, there's this really cool tool called the backdoor criterion, and it helps us spot these potential confounders in our causal diagrams.
The backdoor criterion.
Yeah. It tells us which variables we need to adjust for to get a clearer picture of what's really going on. Like, imagine closing all these back doors in your house, right? You don't want any unwanted information sneaking in.
Okay, yeah, I get it. So it's like we're blocking those back channels of influence to isolate the true causal relationship.
That's a great way to put it.
But this is where things can get a little tricky, right? I mean, because if we adjust for the wrong variables, we could actually end up creating more bias, not less.
That's right. It's called collider bias. And it happens when you adjust for a variable that's actually a consequence of both the cause and the effect. It's like, instead of opening the front door, you accidentally open a trap door and all these like weird creatures come pouring in.
Whoa, okay. That's a vivid image.
It's important to understand those causal relationships before you start adjusting for things.
Right, right. So we need to be careful about which doors we're opening and closing. Now, all this talk about confounders and bias, it makes me think of that, like, classic example, the smoking and lung cancer debate, right? I mean, that was like a major battleground for this whole correlation versus causation issue.
Oh, yeah, absolutely. For years, scientists were arguing about whether smoking actually caused lung cancer, or if there was some other factor, like, maybe a smoking gene that was actually responsible for both.
So the smoking gene would be the confounder in this case.
Exactly.
That's like, are people smoking because they have this gene, and that gene is also causing the cancer? Or is it the smoking itself that's driving the cancer?
Right. And that's a tough question to answer, especially if you can't actually measure the gene.
So if they had these causal tools back then, could they have, like, settled the debate sooner?
Well, it's hard to say for sure, but they definitely would have had a better understanding of the problem.
So how would they have approached it differently with these, like, causal diagrams and do calculus?
Well, for one thing, they could have used something called the front door criterion. It's this really cool technique for estimating causal effects, even when you can't measure the confounder directly.
Okay, so it's like finding a secret passageway.
Yeah, it's like finding a secret passageway that bypasses that main entrance that's blocked by the confounder.
Interesting. So even with incomplete information, you can still get at the truth.
Exactly. And in this case, the front door might be something like, looking at the tar deposits in smokers' lungs. We know smoking causes tar deposits, and we know tar deposits are linked to cancer. So by studying that pathway, you can start to get a handle on the causal effect of smoking on cancer, even without knowing about the gene.
That's really clever. So it's like you're finding a way to, like, triangulate the relationship by looking at the intermediate steps.
You got it. Now, another really fascinating aspect of Pearl's work is his emphasis on counterfactual.
Oh yeah, the counterfactuals.
He's saying that imagination is a key ingredient in scientific understanding.
I love that. So it's not just about, like, observing what is, but also about, like, imagining what could have been.
Exactly. Because counterfactuals, those what if questions, they allow us to probe deeper into these cause and effect relationships. They help us understand not just what happened, but what could have happened under different circumstances.
Right, right. Like, that classic example of the firing squad, right? You're asked to imagine, like, what if one of the soldiers hadn't shot? Would the prisoner still be dead? It really makes you think about the complexities of causation and responsibility.
Absolutely. And then there's that biblical story of Daniel, He and his friends, they challenge the king's diet, and they show that they can thrive on a plant-based diet.
So it's like a real-world counterfactual experiment.
Exactly. And they ended up being healthier than the people eating the standard diet. It's a pretty powerful story.
And it reminds me of how we design experiments today, with control groups and treatment groups, or essentially asking, what would have happened if these people hadn't received the treatment?
Right. And then there's that famous example of the Berkeley admissions bias case. The one where it looked like women were being discriminated against in the admissions process.
Oh, yeah, I've heard of that.
Well, when researchers used causal diagrams to actually account for the confounding factors, the apparent bias completely disappeared. Turns out women were just applying to more competitive departments.
So without that causal lens, they would have drawn the wrong conclusion.
Exactly. It's so easy to get misled by those surface patterns in the data. We have to dig deeper, ask those counterfactual questions to really understand what's going on.
Now, you mentioned earlier that these counterfactuals, they're not always easy to assess, right? Especially in these, like, nonlinear systems.
Yeah, nonlinear systems can be they can be tricky. Like, think of a light switch, right? You have to apply a certain amount of pressure to flip it, and then boom, the light goes from completely off to completely on.
Right. There's, like, a threshold.
Exactly. And in these systems, small changes can sometimes have, really big, unexpected effects. It's not always a smooth, gradual change. It's like that job applicant example. Maybe a candidate needs a certain salary to accept a job offer. So even if you increase their qualifications, it might not actually change their decision if the salary offer is still below their threshold.
Right. So it's like you need to cross that threshold to, like, trigger the change in behavior.
Exactly. So we need to be mindful of those thresholds and those feedback loops when we're building our causal models.
So it's like, even with all these powerful tools, we still need to be really careful and thoughtful about how we're using them.
Absolutely. Now, we were talking about counterfactuals, and I just wanted to mention that there are actually kind of like different levels of counterfactuals. Some are focused on individuals, some are focused on populations.
Well, interesting. So, like, what if this specific person had done something differently versus what if everyone had done something differently?
Exactly. And the individual level counterfactuals, they can be more speculative, right? Because we're dealing with all these like unique circumstances. But the population level ones can be a little more tractable. We can use statistical methods and these causal models to estimate the likely effects on a larger group.
Right. So we might not be able to predict the exact outcome for like any one person,
Yeah.
but we can get a sense of the overall trends, the potential impacts on a larger scale.
Exactly. And that's really helpful for things like, public policy decisions. Like, what if we implemented this new education program? What would be the likely effects on graduation rates? We can't know for sure what will happen to any individual student, but we can use these causal models to get a pretty good estimate of the overall impact.
Okay, yeah, that's super helpful. And as we move from those like individual level counterfactuals to those population level ones, we're kind of starting to bridge that gap between like understanding the why behind things
Yeah.
and figuring out the how,
Right.
the actual mechanisms.
That's a great point. And that brings us to this really important concept called mediation.
Mediation. Okay, yep. Tell me more about that.
So mediation is all about understanding those pathways, the steps involved in getting from A to B. It's not enough to just know that, say, a new drug improves heart health. We want to know how it's doing that. Is it lowering blood pressure? Is it reducing cholesterol? Or is it doing something else entirely?
So it's like finding a shortcut through a forest, right? If we
Yeah.
understand the paths, we can reach our destination more efficiently.
I like that analogy. And when we talk about mediation, we often distinguish between direct and indirect effects. So the direct effect is like the straight line from A to B. But the indirect effect, it might involve multiple steps along the way.
Right. So it's like
Yeah.
it's like a more scenic route. It might take a little longer, but you get to see more along the way.
Exactly. And it's important to remember that the total effect isn't always just the sum of the direct and indirect effects. In these complex systems, there might be interactions or feedback loops that make things a little more complicated.
Right. So it's like those paths might intersect or overlap. You can't just like add up the distances and get the total.
Right. You need a more nuanced understanding of how those pathways are interacting. And that's where causal diagrams and do calculus, they can be really helpful. They can help us map out those pathways and quantify those indirect effects.
Okay, so we're starting to see how these causal tools can be used to like really unpack these incredibly complex phenomena, right? From gene-environment interactions to the effects of public policies to even the spread of misinformation.
It's really exciting, isn't it? And it's just the beginning.
Yeah, I have a feeling this is like the tip of the iceberg.
Oh, absolutely.
And I'm really curious to see where this field goes next.
Me too. It's a really exciting time to be studying causality.
It's really amazing to think about how all these causal tools, they can be applied to like so many different areas. I mean, we're talking personalized medicine, public policy. I even saw some stuff about like using causality to understand the spread of misinformation online.
It really is. It kind of highlights how interconnected everything is.
Yeah. Yeah.
And how understanding those connections, it can be so crucial for pretty much everything.
Yeah, absolutely. Now, we've been talking a lot about Judea Pearl and his work, but you mentioned earlier that this whole field of like causality science, it's constantly evolving, right?
Oh, absolutely. I mean, Pearl's contributions, they've been like groundbreaking, but there's this whole community of researchers out there who are like really pushing the boundaries of what we can know, what we can do with this stuff. It's a really exciting time to be in this field.
So where do you see this field heading in the future? Like, what are some of the big questions, the big challenges that these researchers are kind of grappling with right now?
Well, one area that's like really hot right now is this intersection of causality and artificial intelligence.
Oh, yeah, AI. Everyone's talking about AI these days.
Yeah.
So, like, what does that look like? Causality and AI.
Well, the big question is, can we create AI systems that actually understand cause and effect? Not just, correlations, but like true causal relationships.
Right, because that's how we think, right? As
Yeah.
humans, we
Yeah.
don't just see patterns, we understand why things happen.
Exactly. So if we can, if we can build AI systems that can do that too, I mean, the implications are huge for everything from like robotics to healthcare to, I mean, even scientific discovery.
It's almost like we're trying to teach machines to think like humans, right?
Yeah, that's a great way to put it. And it brings up some really like deep philosophical questions too, like what does it even mean for a machine to understand causality? Could it
Hmm.
ever like truly achieve the same level of causal reasoning as a human?
It makes you wonder, like, is that one of the key ingredients for real intelligence, whether it's, human or artificial?
That's a great question. And, another area where people are doing some really cool work is in applying causal reasoning to like really complex systems, like ecosystems, economies, social networks.
Right, because those are systems with so many moving parts, right?
Yeah.
It could be almost impossible to predict how they're going to behave.
Exactly. But with these causal models, we can start to untangle those interactions. We can identify the key drivers of like system dynamics. And that could help us make much more informed decisions about things like, climate change or economic policy or public health interventions.
So it's like having a simulator for the real world where you can like test out different scenarios and see what the potential consequences might be.
Yeah, that's a good analogy.
Now, speaking of like real world consequences, another thing that comes to mind is like understanding the role of human bias in decision making, right? I mean, we know that our judgments, they can be influenced by all these unconscious biases, related to things like race, gender, socioeconomic status.
Absolutely. And those biases can have a huge impact on, well, on everything from hiring practices to loan approvals to, I mean, even criminal justice outcomes.
Yeah, and it can be really hard to see those biases, to even be aware of them,
Yeah.
especially when they're operating on this like unconscious level.
Right. And that's where causal reasoning can be so powerful because
Right.
we can use it to actually like identify those biases and then develop strategies for mitigating them.
Oh, that's interesting. So how does that work?
Well, you can use a causal diagram to map out like a decision-making process, and then you
Hmm.
can actually pinpoint where those biases might be creeping in. And once you know where the problem is, you can start to design interventions to make those processes more fair, more equitable.
It's like we're using a causal lens to like examine our own thought processes, right?
Yes.
To identify those blind spots that can lead to, you know, unfair or even unjust outcomes.
Exactly.
Now, another big challenge that I've been thinking about a lot lately is like misinformation,
Mhm.
especially online, right?
Mhm.
False or misleading information, it can spread like wildfire on social media, and it can have real world consequences.
Oh, absolutely. It's become a major threat to, well, to public discourse, really, especially in areas like, public health or politics.
Yeah. So where does causality fit into all of this?
Well, causal reasoning can help us understand the mechanisms by which misinformation spreads, like what makes people more susceptible to believing and sharing false information. If we can understand those causal pathways, then we can start to develop strategies to like counter them.
So it's like we're trying to develop a vaccine against misinformation.
Yeah, that's a great way to think about it, like inoculating people against these harmful ideas.
And it's not just about like debunking specific claims.
No,
Right?
it's about building like a resilience to misinformation in general, equipping people with the tools to think critically, to evaluate information, to distinguish truth from falsehood.
It's about empowering people to be more discerning consumers of information, especially in this day and age where we're like bombarded with information from all sides.
Exactly. And as new technologies emerge, things like AI, virtual reality, I mean, we need to be even more vigilant about this, about the potential for misinformation, for manipulation. And I think causal reasoning has a really important role to play in helping us anticipate those challenges and develop strategies to mitigate them.
So it seems like causality science, it's not just about understanding the world as it is, it's also about like shaping the world as it could be.
That's a beautiful way to put it. It's about using our understanding of cause and effect to make better decisions, to design more effective interventions, to
Well,
create a more just, equitable, and informed society.
well, this has been an incredible journey, exploring this world of causality with you. I feel like I've gained a whole new set of like tools for thinking about the world, my place in it.
It's been a pleasure. And remember, this is just the beginning. There's so much more to learn, to discover.
To everyone listening out there, we hope this deep dive has, sparked your curiosity about the power of causal reasoning. Keep asking those why questions. Keep exploring. And keep seeking those deeper understandings.
And remember, understanding causality, it's not just about accumulating knowledge. It's about empowering ourselves to make a real difference in the world.
Thank you for joining us on this deep dive into causality. We'll see you next time.